So our next speaker is Professor Thomas Zurbuchen. Professor Thomas Zurbuchen is a professor of space science and policy at ETH Zurich and former associate administrator for NASA's Science Mission Directorate from 2016 to 22. During his tenure at NASA, he led the agency's science program, including the James Webb Space Telescope, Perseverance Mars rover, and Parker Solar Probe missions. Before joining NASA, he was a professor at the University of Michigan for over 2 decades. He holds a PhD in physics from University of Bern and has authored over 200 scientific publications. At ETS, he focuses on developing innovative approaches to Earth observation and space science applications. With great honor, let's welcome Professor Zurbuchen.
I want to just tell you what an honor it is for me to be here today. It's the capital with the coolest name in the whole world. I mean, Bern, who knows what that is? Sofia is where it's at. I also want to just tell you how excited I am to also see my colleague here, Luc van Gogh. I learned a lot from. And just also his colleagues, some of them are the biggest advocates for this country that you've ever seen. I've been in multiple meetings with them. And of course, therefore, I know about the excitement of this project that you're working on. And has been great to be here as a result of that. What I want to do today is give a talk that talks about two things that I've been working on in my life. The first one, as he just says, I'm in Switzerland. And whenever you're in a country, try to figure out what could you be doing that not only is good for your country, which is good, but it's good for the world. And so I'm really excited to be talking about a project that we're starting. It's highly complementary to what you're doing here. And of course, the reason I'm talking about it is because we're excited to explore possibilities of perhaps collaboration. The second thing I wanted to do as an introduction is just to tell you how AI has or is affecting space missions, not only from the data side, but for the operational side. And so for me, those are the two things that I want to talk to you about. My hope is you walk away from this talk and basically convinced that Earth observations, which of course you're already working on, is one of the prime places to of applicability of the kind of technologies that we just heard about. Not only because it's really useful, but it's really important. And frankly, some of the challenges that we have, we cannot address without them. That's what I'm going to say. So now you can do your emails if that's what you want. Just kidding, of course. Again, I grew up in Switzerland, and that's where I'm going to end up. So I'm just going to tell you where I started off. If you stand at the town where I grew up and look out over the lake, you see the mountains and you see everything that's important. First of all, you see the sky, where all his planets live. The exoplanets, and frankly, I love the sky there because it's so dark. As opposed to in Zurich, where you barely see the planets. I saw the Milky Way, and I saw a lot of stuff. I spent a lot of time under the sky, which of course had to do with me studying astrophysics and learning about this. But we also see is the amazing geology, which is the Alps. And the geology really affected your life. What you don't see on this is during my time when I went to school at down by the lake where my schools were, there were twice incidences where I could not get down to the valley because landslides came and covered up the roads or pulled out the roads entirely. And frankly, I'm going to talk to you about that problem, which has huge applicability there. One of the things that Switzerland has, it's very close to some of these challenges that, of course, are there, have been there for many decades, but are amplified because of the fact that the world, the climate is changing. And so as a result of that, that's what I hope you see out there. The reason I started astrophysics is actually not primarily just because of looking at the sky, it's because of stories. And stories like this. This, of course, is a drawing by Galileo Galilei, who got a little toy from Amsterdam and looked through it. It's just two pieces of glass and a tube. And he looked through it, and he looked at Jupiter, and what he saw not only changed what we know about our solar system, but it changed how we think, not just about the solar system, but ourselves, which is the exciting part of science. That's what I've always loved about science. Not just about knowing, it's about thinking differently. Of course, what he found is that Jupiter, against what the popes and the kings said, actually had celestial neighbors that rotated around it. During that time, every school, every place that you would go, people told you that everything is going around the Earth. Clearly, there were exceptions. And the planets, the moons of Jupiter, as they're now called, the Galilean moons that he observed and he drew there, opposed that. That was a dangerous thing to say because he flew in the face of, as I said, the kings and the popes. And so basically what happened, of course, it changed his life, not for the better, because he was locked up for a large fraction of his life. Nonetheless, he made history, and by the way, you can go visit these places now, and you can go visit with spacecraft that fly through it. One of these spacecraft in 1995 to 2003 that flew by is named after Galileo in honor of these discoveries, and it basically took the pictures that I'm showing you, not only of Jupiter. It's red hurricane, that is that spot that you're looking at, by the way, which was discovered about 100 years after Galileo and has been weakening ever since. So yes, you're going to see it, your children are going to see it, and then, it's getting weaker and weaker. The sky changes, not just the Earth. But what you also see are these moons that are really exciting. Io being a volcanic world, and Europa being a surprise in its own. It looks kind of ragged. It looks to everybody who's looking at it like there's a surface that is changing. By observing on Galileo, we actually saw that it's changing at the time scale of the mission. It's cracks. If you stood next to a glacier and observed every day, you'd see that the cracks are changing too. That's what's happening there. The biggest surprise, though, came when Galileo flew by Europa, and it flew by Europa, and the Jupiter magnetic field, which is much stronger than the Earth, but also bipolar, like a dipolar field, just like the Earth magnetic field, roughly, that changed substantially in the vicinity of Europa, and it shouldn't have. Well, it shouldn't have because we were wrong about what we thought this was. We thought it's a rocky thing with a surface that has water or ice on it, and it was entirely different. It changed because it's a dielectric underneath the surface. A dielectric we call water, which is underneath the surface and of course changes as it's moving through the magnetic field, the behavior of it. So this world is a really exciting world that looks like this. This is from a later observation and has a lot of patterns. And the question is, how do you observe this world in the context of a question that is just as surprising as Galileo looking for the first time? Concept of a question which is, could this be a place where life can arise in the solar system? Not just on exoplanets of the type that he is interested in and he wants to investigate, and his colleagues, but a question, how is this a place where habitability of extant life could occur? To do that, you don't just need a toy from Amsterdam, you need to go a little bit bigger. Here's the tool.
Live at NASA's Kennedy Space Center for NASA's Europa Clipper mission, a nearly 2 billion mile, 5.5-year journey to Jupiter's icy ocean moon.
And liftoff. Liftoff of Falcon Heavy with Europa Clipper. unveiling the mysteries of an enormous ocean lurking beneath the icy crust of Jupiter's moon, Europa.
Side booster separation confirmed.
Fairing is separated, and those will be recovered by SpaceX's own recovery ship, Go Cosmos.
This is a big moment for the program, for NASA, APL, and JPL. Let's watch.
Europa Clipper, separation confirmed.
And there you go. NASA's Europa Clipper probe, embarking on a long-awaited mission to study Jupiter's icy moon, Europa.
So now you say, what does that have to do with AI? Now I'm coming. So the issue is, if you go to Jupiter, what I told you there's a strong magnetic field. What I didn't tell you is something that Frank Drake figured out in 1959, before we ever went there. He figured out, looking at radio waves from a pretty simple instrument, that there's a lot of radio noise that could only be explained by high-energy particles that he interpreted are really a belt of radiation, very similar to the Van Allen belts around the Earth. And so basically what you have to do with a spacecraft of the type that I just talked to you about, you have to fly in this belt, and it's so terrible to fly into the belt that actually you cannot go into orbit around Europa, but you have to come in and out of Jupiter, kind of to go recover. Before you do that, if you just stuck into orbit around Europa, which you can dynamically, but if you tried to do that, you would die within months. Just the electronics cannot take it. What the electronics also do when that happens is even worse than the computers that we have here. They have hiccups constantly. So what you have to do actually to fly that spacecraft is you have to build in intelligence and pattern matching of certain phenomena and kind of tell the spacecraft to act autonomously during that. Because of course the speed of light is really fast if it's measured in this room, but it's really slow if your spacecraft's hanging out at Jupiter and you have a problem. Because it's like hours until you know what's actually going on. You need to act. So real-time judgments are required to actually enable this mission. And prolonged communication blackouts necessitate AI-driven models and autonomous decision-making. They're much simpler than what he just discussed, much simpler than the models you're working on here. But nonetheless, that integrated in a rudimentary fashion has really changed the way we're doing space missions. Not just there, also landing on Mars, for example, where all these models are basically being used in a direct fashion already. What we have done, though, generally speaking, still, we don't trust the models fully. So basically, if it's a severe decision, what the model will do is tell the spacecraft, stop doing and listen to Earth and do what they say, because we don't trust the model enough. But we're getting there, and basically many of the decision processes and missions actually have AI enabled now, and are there in modern systems. So with that, what I want to do now is go back to the Earth, and of course recognize that the Earth, kind of to everybody's surprise, after we went for very different reasons, left the Earth for very different reasons, namely to go to the moon, to have humans there to compete in space. Being in space has been the coolest thing for our planet, because frankly it turns out the most important observation platforms we could be having to understand our planet, not only locally but globally, come from space. And of course the challenge there is that the Earth observation data types are very varied. You of course know about imaging, Google Maps or whatever your favorite, Google Earth, whatever your favorite software is, LiDAR, which tells you the position, for example, of water, and basically the level of water, ocean sea levels, at the accuracy of fractions of millimeters, kind of with average. And then spectral data I'm going to talk to you about, which are at the process of fundamentally disrupting how we're imaging things today. The spectral data were used in places where you need to find green tanks under green trees. That's where people started developing the technologies, but that's not what we're using it today. But what's happening there is literally the data are multiplied by a factor of 100 to 1,000 that a given spacecraft can collect. And what we're now trying to do is not only get the data down, but actually use the processes and systems that are being discussed on the spacecraft directly. I'm not going to talk about all of these things naturally, but kind of my point is the way we have done these systems, and having been responsible for NASA's Earth Science program, the way we have built the data systems is very much sensor-centric. Every sensor, every instrument has its own database. They maybe all look at water, let's say, or 10 databases may look at water, but they're not looked at together because of the funding model and various other obstacles we can talk about. But what we need to do is look at the data challenge in a totally new way. Let me define a data challenge. These are the European missions that are flying in space or are being planned. The best program to observe the Earth as a planet is worldwide, is the Copernicus program. I always say it like if we were in Switzerland. I'm so glad you're here, Mr. Ambassador and Deputy Ambassador. But I always tell people we should not join Copernicus because it's European, because it's the best. Also because it's European, but it's the best program, is my point. There's many other spacecraft that are out there. About 80% of forecast power in many of the areas come from space today. And you already know, of course, you're following this, that kind of AI models have already beat in many of the applications traditional physics-based forecasting models in terms of applicability. The challenge we have already outlined is that in any one of those domains, if you want to really understand what's happening, you need to pull data from different spacecraft. You need to pull data from different data types. Some of them are time series of the type that we just heard. Some of them are highly complex vectorized spectral data. Some of them are gravity data, which are really complicated, in which you measure the distance of spacecraft relative to each other to within atomic diameter. And so basically, because the gravity is not uniform on Earth, that distance changes, need to deconvolve. So you need to bring those together to do the science. And so basically, if you looked at NASA, you basically said, let's talk about the data we have. Right now, there's about 150 petabytes of data, and we're on the way up substantially. By the way, we launched 2 missions. NASA launched 2 missions during the last 2 years that by themselves have more data than all the other 30 plus before, because we're taking advantage of some of these evolutionary things that are there. Europe, the only mission has ever had a GPU in space. Europeans did. And so it's really not only using AI on the ground, but using it up there. And so basically the challenge we've had is frankly that by our estimates worldwide, there's less than 5% of the data somebody ever looks at. And the simple reason for it is the graduate student model, which I grew up with. Like you walk into an office, your professor says, here's a directory, do research. That model doesn't scale. Kind of without, even kind of the programming version that I did, does not scale. By the way, what I want to tell you, the vast majority of spacecraft that are out there now are commercial entities. Kind of if we saw out there and we counted the spacecraft, we could see every spacecraft that flying over us right now that's looking at the Earth, it would be in the sky at a given time of the order of 50 or so spacecraft just at that instant, at this moment in time, but rapidly increasing. So basically what we have is the data are going up, and that kind of disconnect, so to say, of both the need of what the data are to how we analyze the data the methodology really changes. So I want to show you an example first, not in Switzerland. And it has an example that has to do with Puerto Rico, with a hurricane that swept over it. So what you're going to see is an analysis which is entirely using the type of models that I'm not going to talk about because Luke is so much better at it, as many of you are. But basically how these models are helping in a direct fashion. This is Puerto Rico. This is basically the overall distribution of electricity, light at night over that island, which tells you where electricity is. This is the track of the hurricane. And then at subsequent nights, you saw once the clouds were gone, how much light was there, how much light came down. All this stuff was done, frankly, you have to train an AI to do it, right? It's many, many different images that come together. What you can do then is basically do a distribution of days without power. And, you know, so you look at this and of course your heart breaks because you think of the students that lived in this other part of the island and there was no school. Or no real infrastructure available for many, many days, sometimes 100+ days. And so basically that's an application. So I want to tell you now application, kind of what I'm going to do is actually go bottoms up. To show you that, what I'm going to start is on a helicopter. And so what I'm going to show you is the Swiss mountains. You have beautiful mountains too, so you can resonate with that. This is Swiss mountains. This is in Canton Valais, so it's in the south of Switzerland, and you see up there kind of a multitude of things. By the way, again, looking out the front of the helicopter, you see, of course, ice. You see a lot of gravel, kind of rocks that come down. Remember, gravity always wins over time. Everything wants to go to the lowest energy state, so it's just going to come down. You look at this and you say, wait, what is this? Is this just rocks? No, this is 50% ice covered with rocks on top. So you basically look at this and you immediately look at it with your eyes and say, this is not stable. You immediately know it's not stable. Yeah, it's not stable. And by the way, there used to be a glacier back here. So let's see what happened to it. This is, as I said, something like a couple weeks ago. This is, there was a glacier up there, and what happened is people followed that glacier for a while, but all of a sudden it turned unstable, and then a landslide went on top of it, and the glacier exploded. What is underneath this cone is a whole town, a beautiful town of Platten, with some of the roofs you see in the water there covered. You basically say, well, why is it still so much water there? Well, I told you earlier, 50% of the rocks that came down are ice, and the ice is melting, so there's more water coming from the bottom. The one thing you see when you take a helicopter up, you stand in front of that wall, it is still falling. It's not done. And so basically, this is one instant. You basically say, like, was it predicted that that could happen? Yes, Platten was one of the top 20 or so areas that were identified as a danger. And in fact, the science and the measurements were so good, they put measurements up there that unfortunately, one person died. But let me say, fortunately, hundreds of lives were saved before the thing came down. If you asked before, and I'm going to show you the name of the person I'm quoting because he's my hero. He's the guy who's basically in charge of issuing those warnings. If you asked them what are your top 10 risks, was Platten amongst them? The answer was no. Because there's many other areas. By the way, this is the landslide from a slightly different direction. You see how the water is tunneling through, and with it bringing the gravel down the valley and creating problems elsewhere down the valley. So if you looked at other places, this is not by itself a risk to humans, but it's one of the biggest. It's the biggest glacier in Switzerland, and basically what you see at the top, kind of a lot of the the ice being destabilized under the force of gravity and warming, and you see the breakoffs that are there that are also being monitored. In this case, it's not because the ice is actually killing people when it's coming down. It's the secondary effects that are coming down. You should know, for example, that any water power plant, hydro plant in the mountains, there's something like a dozen landslide cones that need to be observed for safety of the wall. It used to be only 2 as of on the average. It's now dozen and often dozens, because in the backcountry, if something happens and it starts jamming, for example, some ice comes down, water goes behind it, that water falls through, it basically can rip off the entire system in the valley. And so basically, I don't know what you know this town, but I took my family skiing there, and that's where they fell in love with it. That's Zurbuchen. So you down there, and I recommend you should go there because of Dr. Mayora and others who keep you safe, but not because kind of above the mountains it's not scary. So this is a glacier above the mountain which is being monitored. This is about 1 meter per year going towards the cliff and coming off, and it's really hard to predict when it's coming down. By the way, the one I showed you looks a little bit similar to that. This has nothing to do with climate change. In this case, it's just a wall that went unstable under the force of gravity. This is the one have been dreams about. Do you see this big rock here? That is, if you were in Zurbuchen and you looked up a little bit diagonally over, up above, over the cliff, that's where it is, and it's moving towards the cliff. This is like a 4-story building, and it's moving towards the cliff at the speed of 3 meters per year. So it's going to come down, 100%. Because gravity wins, remember? Everybody will be safe because they're monitoring. Do you see the measurements sitting on top of it? But the buildings down there will not be safe because it will surely go across the valley. Every year, buildings, not only roads are destroyed, but buildings are destroyed as a result of that. By the way, I'm telling you about Switzerland just because I live there. India is the location of the biggest kind of death rates of landslides because of the same effects in the back valleys coming down. So basically, when you look at this problem, and now I'm going to go back to space, and you basically ask the person in charge of risk assessment, what do you actually do? He says, we have hundreds of hotspots that we're monitoring. Some of these sensors are 150,000 euros. Some of these sensors are just a few hundred, and you saw some of them. We're monitoring lots of them. He said, what worries you? He says, in the last 10 years, the majority of problems and big disasters came in areas we didn't observe. So they come out of the darkness of the part we did not look at. So what we need to do is actually have alpine surveys to detect movement patterns, plus advanced cost-effective drone and landscape sensors that can support this. And so the question is, can you build that today? And of course, the answer is we sure have to try, and I think it's possible. The way we're doing that, just before I go into what we're trying to do as a solution, I'm just going to talk about the forest. I don't know whether you know my last name. It means by the beech tree. Beech. So like apparently my relatives in the past lived by a tree that has been identified. Remember I talked to you about hyperspectral imagers. This is a hyperspectral imager, in this case on a drone. Not only can we, in one image, in one shot, and trained by AI, using the very models that we just heard about and the models you're working on, we can identify every tree type, not only location, but also its growth patterns over time if we do it multiple times. And in addition to that, the overall health of the trees. Because what we know is a healthy tree, of course, does photosynthesis. From space, we've already shown that. We just haven't scaled it yet because we used the grad student model, which I told you is not working. But basically a tree that stops doing photosynthesis has a different emission pattern. And we can actually tell which trees are healthy or sick before they turn bad, before they fall over, or because before their leaves turn yellow or whatever. So this is an application of Greece at the university where I work. I already talked about these things. So basically, what we're really trying to do using the mountain application and others application is really what I call use the kind of rapidly increasing space data and the Switzerland in its advantages. Okay, so Switzerland is small. It's much smaller than where we are, and it's highly more instrumented than most countries. If you look at sensors per square kilometer, like Switzerland got you, there may be the Emirates also, and others like that. But kind of if you want a diverse type of environment in mountainous areas with farming and so forth, we have the sensors, right? So what we're trying to do is make Switzerland kind of recognize we need to know these things because of the dangers that come from it and the opportunities. But we think Switzerland is an ideal test bed because of its diverse terrains and the high data density we already have. And so basically our goal is, in this case, not to write papers primarily, but to find solutions to go all the way from space to mud. So go from deep space where spacecraft are roaming and sending data down to data that are in the hands of geologists or data in the hands of farmers that support their decisions. That's the opportunity we're going to go after. And what we did is we started, just like you have, kind of building a center around that idea. We call it the Swiss GeoLab for all the reasons that are obvious now. And really, our goal is to use the abundant space data and the practical solutions that create economic value and address Switzerland's most pressing challenges. I'm talking about economic value in the following sense. You know that roughly half to 3/4 of all fertilizer that's put out in fields is not necessary. We put way more fertilizer out than is there. So there's a farmer. I grew up in a farm village. I already showed you. They're not rich, the farmers. What we want to do is help them save money. Only use the fertilizer where you need to. Because guess where the other fertilizer goes? Into the lake that I showed you and down the river. And it's creating environmental hazard. So economic value is not just kind of top level. There's other applications you could create economic value, but we're thinking about these win-win solutions that are there. And we think Switzerland has a unique opportunity. That's what, kind of to be part of that ecosystem that you're all part of as well. And of course, that's what we're going to do. It's kind of that's what's going to be hard. Everybody who's ever been in a university knows what's going to be hard. It's easy to set the first one. We want to be a standard for space data to calibration. By the way, we've already contacted basically all space imaging companies and basically say, I want to do that, help kind of move in with us. And we have very positive echo, in some cases even MOUs, that they basically want to give us the data, so kind of for us to kind of help with the calibrations, so their models are doing well. This one is important, though. We don't want to measure the success primarily by number of publications, but by really the success of going space to mud. The usefulness of AI allows us to actually help in a much more focused fashion than a generalized kind of global fashion. Like politics, as we say, all climate change is local. And so we need to be able to do that in a direct fashion. So we're not going to solve all problems. We're going to focus on a handful of problems for the money we have. Kind of in round numbers, it's 200 million euros that we're going to spend on this in the next 10 years. And of course, there's some applications that we're going to also deploy drones and kind of interface between the space data and the ground. Drones and sensor networks. We're working with companies. We have a lot of drone capability there, so we're excited about this. We're launching this year. We just announced the director, the guy who's coming to run this, used to run all of research and analysis at JPL until last week, basically in earth science. So he's coming to, he grew up in Switzerland, and just like many of you who went somewhere else and are coming back to your home country, we're doing the same, taking some of our best back in our home country. There's a team that is starting to look at this. It's not that important who they are, but I think the one thing I want to talk to you about is, of course, what's beautiful about this amazing time we're in which these technologies that you're all focused on are making such important impact, is that I do believe ultimately what it helps us to do is take advantage of the assets that we have, both in space and on the ground, to kind of help preserve and keep beautiful our amazing, most beautiful planet. None of the planets that we've observed anywhere else is as beautiful as we are, and none of them is as much linked to our destiny as this is. So we're excited about this. This is, as I told you, Dr. Mayura, who is the guy who is in charge of all the risk assessment of that part of Switzerland, and the guy who I did the helicopter flight with. He's my hero, because ultimately he is the person who is at the interface of science and saving lives. And I would humbly suggest that that's what the analysis of the important models that you're working on should be also, at that interface of enormous technological progress in space and lives and values right down here on Earth. With that, I'd like to stop and answer any questions I might. I just want to warn you, usually I'm a professor, so I call on people if there's no questions. Just kidding. Thanks.
Thank you very much for a very insightful talk. With that, we're open to questions.
Nobody's looking at me.
Seems like everybody getting ready for lunch. Okay, I'll pass it there.
Yeah, congratulations for GeoLab. Seems like a very, very interesting a new company. You talked about having drones flying over and gathering data. That sounds very exciting to me. Is there any plan to release this data, or it's going to be Swiss-owned?
Oh, our goal, so by the way, what we're doing right now, what I didn't tell you, but let me tell you, what we're doing right now, we're putting a lot of money into the computational infrastructure. So we're creating a big data kind of server with hot and warm storage right next to the Alps computer, that's how it's called, which has something like 11,000 GPUs. You know, like what we're really trying to do is take advantage of that investment that's there that was not us. So what we're going to do with this, absolutely, we want to, for us to be the standard means we want to put the data out. The way we want to use the drones is really to be as kind of a partner to the space company. So I don't know what you do exactly, but I know there's a really cool space imaging company here in this country, Enduro, you know, and what we're trying to do, and I've already met with a lot of companies, basically said, look, give us your data, we're going to give you the calibration data. So together, let's go develop these systems, come move in results. Once we find the right calibration, use it and scale it, because the world gets better if you do. So we're transcribing to an open data policy as much as absolutely possible. The only caveat that I have at this moment in time, we have still a few problems to solve, because what we're also trying to do is work with companies, and what we're trying to do is make sure that some of the things that they invest in, they can also benefit from. But there's good discussions. By the way, when I was at NASA, you know, what I felt was I thought this was really important. Like, so we made all the data public already at NASA, the whole policy. That's why we have a lot of data. Europeans did the same. Japanese did the same. The second thing we did after making the data public is we actually started partnering with the commercial partners. So I started buying data from commercial partners, and we had to go through the same thing. And I basically said, if the data are not public, the deal is off. Some data, you know, figure out which parameters. The deal we actually cut over beer in Germany, like some 2 US guys over beer in Germany, and we figured out how to do it, and that's what the standard is today. in terms of data latency. That's what the key parameter is. But still, the data are public at the end. Because I'm a strong believer, even though here the number of publications is not the primary metric we're after, every science needs to be verifiable. And so for that reason, the data need to be out there, because I want you to, if I'm doing things wrong, you need to tell me, because we're all on the same planet. Let's go fix the models the right way. So yes, we want to make it public. In part, the reason we want to focus on drones really quickly is a lot of the data sets that I talked to you about, like all these hyperspectral imagers, they're only coming in the next 2 to 5 years. So the first civil hyperspectral imager we launched 3 years ago, we spent at NASA about 100 million on it. I stood next to a production line of hyperspectral imagers just a few weeks ago, where each one of them, same technology as the NASA, was less than 10 million. And so basically what happens is countries can buy them and put them up. And if we share the data, right, we can really take advantage of this. So the data actually goes exponential as we go. So we want to go ahead and start using the hyperspectral measurements and kind of start preparing some of these calibration things before the data are in space.
That's awesome.
Yeah.
Other questions?
Hey, thanks for the super lecture that you presented. Just want to ask, this project seems like POC, proof of concept. Are you going to excel it for the whole world, for India, because of the steep mountains?
So look, I mean, each one of us has to set up the problem the way they think they can be most successful. In this case, for this project, we're unapologetically Swiss. Mm-hmm. And the simple reason for that is we want to take advantage of this as part of the overall, kind of ecosystem. I want to tell you already now, we're already talking to India. And the simple reason for that is what you're implying. A lot of what we're learning there we want to apply in India. India and Switzerland have a lot in common when it comes to mountains and the terrors that come from them. And they're less instrumented per square kilometer than Switzerland is. So for us, we want to do that and work with India and some of the other kind of areas as well. Yes, so we want to do that. We want to, however, support that kind of translation through the support of companies that can do that, because see, companies scale a lot faster than academia does. I just want to know, and so we're going to take that advantage. So that number of, he sold a startup, so did others who are in the room. So for me, we're going to really kind of actually move to a place away from Zurich where we can put startups right next to it, and which we give them the access to the same data ecosystem. And so yes, we want to scale through this or through collaborations that we're funding elsewhere. We already have interested parties, but this one will be very much focused on just a handful of problems. That's what we're going to focus on.
Thank you very much.
Thank you very much for this very interesting presentation and for mentioning gravity. Actually, we are working with the GRACE data, and this is actually a very fantastic data source. The only problem is it does not have resolution, so I've heard that NASA is now working on really new technology which is going to really scale it up to 10-15 meters, which will be really breakthrough. But we will need to wait for the coming 10-15 years. Thank you also for mentioning Switzerland. I had a chance to work in Switzerland as a PhD student 20 years ago. And in academia, actually, it was really fantastic because I saw how weather and climate was really supported for a very long time, over 10 years financially, so that, damages what you have mentioned could be prevented today, could be forecasted. And I think Switzerland really is an excellent example how investing in science and education and really bringing the networks which are responsible for observation, modeling, and impact can work together on a national scale. This is really very good because, you know, I agree that science or university doesn't scale, because if you're doing what you're doing, that was what 20 years ago was on the table at the universities. So it is really great that, you know, this knowledge and what has been observed and the high resolution data which you are mentioning, which are a golden mine, but you know, countries like Switzerland have this golden mine, countries like India do not have those golden mines, and you know, that's why, you know, I'm not really sure how this can happen, that you can scale it. I mean, some things will be scalable, other maybe not. But the question is here, we are here in Bulgaria and we have the same topography, but not the same investment in science. And, you know, I'm working at university and trying to build a generation of scientists and Earth system scientists which work with this. And my question is actually, you know, what you're talking here today, AI is really old news. But can you say something about quantum computing and its application in, you know, earth sciences or in general? What your, you know, opinion on this topic is? Thank you very much.
Really appreciate it. You know, it's kind of funny that the beginning where you start talking about gravity measurements, you know, the actual way to get high resolution data of the Earth and gravity measurement is through quantum sensors, which have some really important analogs to quantum computing, but are very different application. It's way too expensive to do this in pairs of spacecraft. A quantum sensor you can do individually, directly. By the way, just as a side note for that, kind of to mess with our mind. So the best clocks right now that we have are accurate to within 4.5 hours of the age of the universe. If they're 10 times better than where we are today, we can use those clocks to measure gravity at the level as Grace has that you rightly talked about. So I'm excited about that. You know, developing these clocks to kind of really transform the Earth. Quantum computing, of course, is being worked on. Very much the biggest investments right now. There's governments that are investing. You see, of course, a lot in China. You see in Europe, kind of investments. In the US as well. In the US, I would actually argue the best investments are in companies that are pulling things together. Quantum computing, of course, has tremendous consequences for some problems. Turns out if I want to hide the access to my bank account, I worry about quantum computing more than I'm excited about quantum computing in the context of physical models of the Earth, where actually not very good models have been found as of yet. So at NASA, I had a quantum computing center as part of it. And so kind of, I think I would just say that that's not the final answer to that. I think quantum computing could be really important in some of these applications, especially in the context of some of these models that are being developed here or elsewhere. But also with AI, yeah, people have talked about AI many years, right? And so that's why I showed some of these technologies that are certainly quite old and even so understood that we're putting them on spacecraft where we're betting billions of dollars on it, right? But we're still, you know, we still haven't kind of fully taken advantage of the potential that AI offers in these things. I would just argue in the example. Quantum computing will be similar. Once it's really there, we're going to be full of surprises, because I just really, like I talk to, like, you know, there's these people that are hired by consulting firms and they're envisioning the future. And it's funny, like you do individual meetings with them, how different their futures look in each one of their minds, which tells you we just don't know. But we need to, of course, develop it and start learning how to use it. And I look forward to that. As I said, my favorite application of the whole quantum revolution that is happening right now relates to measurements of the Earth and measurements of the nature around us. That's just absolutely exciting if we can do that. And I think it's certainly, I mean, this may not mean my reach, but certainly in the reach of many of the people who are kind of at the beginning of their careers, that these data are actually available in the next decade or so.
Yes, thank you. And you're right, actually, weather and climate was taken out by AI, by surprise. But you know, they are doing really good job in
that's true.
picking up.
Hello, many thanks for the wonderful presentation. Just before 2 weeks ago, I was in contact for some months with your WSL landscape observation colleagues.
All right.
Yeah.
Wonderful.
I hope you're in close collaboration.
Yeah.
They are landscape ecologists.
Yeah.
Are they optimistic or skeptic for the AI opportunities? Do you have?
They should be both. They should be both optimistic and skeptical. I mean, that's what good scientists are, right? I mean, they should be
are
both.
good scientists.
Like, we have to be optimistic. They're good scientists. So look, I mean, I just talked to the whole leadership team. You know, will we achieve 100% of what we're hoping? The answer is almost certainly no. And can I just tell you, I don't care. I'd rather achieve 90% of a big goal than 100% of a small one. And so what I'm trying to outline is really a stretch goal in which we have a lot of advantages in our favor. And we're going to need everybody, including WSL, to actually, because many of the sensor networks are there, and for what it's worth, right, they're on the innovation side of the government. There's also on the environmental side of the government, there's also networks in other cases. And for what I've been trying to do is actually work with government officials, including some of the ministers, and basically said, look, we want to work together with your teams. It's not a competition against each other, it's a competition for solutions. And so let's go run to the hill together, right? And then frankly, I don't care if they win, but let's actually do these kind of things that we haven't done. Let me just tell you a sad truth. Right now, every day, LiDARs are flying over the Swiss mountains, probably something like 100 passes. How much data do you think of these radars?
100 passes per day?
Yeah. You know, with all the spacecraft that have LiDARs on it. I had at NASA 10 myself, and 10 the Europeans have the same or more. So I just wanted to tell you, how much of that data do you think is being used in by the part of the government that are building maps and are actually updating these maps? And of course, you know the answer. Basically, almost nothing. Because they have their own method, which is a beautiful plane that you can go visit. And, you know, I mean, I love planes. But, you know, like, so you fly every year over half of Switzerland with high accuracy with a LiDAR that is probably a little bit better than the one in space. But see, part of me trying to kind of drawing that image is also to just let's catch up. Let's catch up with, like, just because we can do it doesn't mean it's the right way to do it. Do you see? Because it's not compatible with a future in which many more data will come from space. There's one aspect I didn't talk about at all, which has to do with national defense and security, where a lot of applications of this technology here. That's not what we do primarily at ETH, but that's another reason it's really important for us to kind of pick up and move.
Thank you.
Thank you.
Okay, thank you, Professor Thomas. And you mentioned that Switzerland is the country for data density. And yeah, I've been to Switzerland for orienteering, a kind of sports. And
yeah,
so I'm wondering if it's possible to use Swiss image and Swiss topo and AI for automated orienteering mapping for cartography. Because I think it's for now it's a field that has not been fully explored, and if we have a solution, it will benefit in real-world applications.
So I love that idea. The answer is yes, we should really try and figure out how far we can go. And you use the exact, I did not use the names of the organizations. You used the very names that I actually told the story about. So yes, it's those. The point I'm trying to make, you know, if we want to kind of adopt new technologies and approaches, sometimes you also have to learn to give up old ones. And sometimes that's actually harder than adopting the new one. Giving up the old one, especially, and remember, I have a lot of government background, not so much in Switzerland, so I'm not criticizing the Swiss environment, but that's what the struggle has been so often. So sometimes we're highly sub-optimized to what's possible, and so my hope is kind of by really focusing on one of these problems very hard. By the way, much of this money comes from private. More than half of it comes from private donors. It's not government money. And the reason we wanted, that was so useful to have a private donor is because we can kind of be more unapologetic with some decisions, right? We don't need to do good for all people. But your point is, certainly not at the beginning, right? Your point is very well taken, and orienteering is a cool sport. It's much more like life than a 100-meter dash, it turns out. You know, most of the time you don't know where you are. At least I don't. Yeah.
Hello, nice presentation. So my name is Shwev, and I'm coming from India. So where I'm come from, it's from Himalayan range. So every year we have around 100 or 200 casualties because of extreme rainfall or landslides. Yeah. So what we are currently working on, like fusing different satellite data, like wind speed, land surface temperature, NDVI, LULC, and fusing them to an AI model. But what I think is not just on AI, is it the possibility that we can fuse both AI and physics-based numerical weather prediction together to forecast some rainfall or extreme weather forecasting?
Yeah, I mean, what you're talking about, right? Rainfall. By the way, I just want to tell you, of all the forecast kind of parameters in meteorological systems, rainfall or snowfall are the worst. Yeah. And you know why, right? Kind of it's a critical event, kind of like molecules have to come together around an aerosol in the right environment, and kind of making the predictions are really hard. But you're right, kind of the right way to do it is have the novel, and there are novel technologies for that, together with physics-based models, because otherwise the parameter space is too big. So probably that's what's going to happen. By the way, I'm sure you're thinking about it, but for some of the applications that you're working on, I'm sure the NISAR spacecraft is on your radar.
Yeah. We are working. We're taking the data from the Copernicus using Google Earth Engine, but still, to get the data are usually very coarse, not fine-grained. Yeah. Like to get like 0.1 degree or 0.01 degree resolution data, it's hard. It's usually interpolated, and like it's difficult. Even though we fit this data into AI model, like we are not able to achieve like that much good results.
Yeah, that's exactly what the status is today, right? Kind of, I mean, there's very few groups. We probably know them all. That have high-resolution models with enough computational capability to do this. Your instinct is really correct, but we need to kind of make progress. You know, one of the advantages of AI that I have not talked about is it's really successful at compressing data. Like, I mean, there's papers now out that show in many of the geophysical data, 5% of the data have 95% of the science that we want to look after. And so kind of some of these tricks, right, will also help some of the scalability that limits what you're just saying now. I agree with your statement.
Yeah, thanks so much.
Trying to make it even, huh?
Thanks for the presentation. Well, it seems like a lot of fantastic technologies will come out of GeoLab. What is the kind of the entrepreneurial vision behind it? Do you want to commercialize some of these technologies as well, or is it just going to be sticking mostly within the same lab and within the companies that are supporting it, you think?
Yeah, so what we're trying to do kind of around the sectors, I mean, what was already in some of the questions, we have some government labs that are doing amazing work. We don't want to duplicate what they're doing, like we want to partner with what they're doing. But what we're actually trying to do is partner with both companies, but also kind of in an environment, we also train the students kind of in a startup kind of world and really co-locate them in this environment. So our vision is to really create a cluster for startups. So if you want to work in this environment, you come work with us for a while and then go wherever you want to build your company. Kind of, we really want to use it as a kind of an attractor for some of these models and systems, and kind of allow us for that. Without the entrepreneurial scale, it's not going to be successful. So I actually, it's not just I would like to do. I think it's absolutely necessary, because otherwise we're going back to a few papers. So it really needs to scale for it to do what we want. And so yes, partnerships with companies that are already established, but also new partnerships matter. You know, it's really interesting. This is not what we usually do as academics. I showed you the helicopter, not to kind of show off the helicopter. I hope you got the underlying message. To actually figure out what the problem is, you need to talk to the people who handle the problem. Kind of most of the important answers are not found in your office. So for me, that's the underlying image. That's why I'm showing you this stuff. And because frankly, I think of this problem as helping Dr. Mayura. There's science, but for me, success is that him and his team basically say the world got better because of us. Well, that's very much how companies think, right? It's a customer focus, much more so than just a problem focus. Yeah.
Okay, also, this is also lunchtime mostly, so I guess we can stop here. Except I have one follow-up questions following the other. Most of the questions arose was like, what if you are not Switzerland and don't have similar density of the sensors as well as amount of compute? Then what to look for? What to look forward? What future is bringing? That are things getting cheaper in these acquisition types? So it's going to be different kind of sensing systems going to evolve over time. As eventually it becomes affordable, or same thing also regarding the AI models. These not need to be trained. What is your take on this? That what to look for countries which are not Switzerland?
Well, so we're here in the country we are. This center that you have, I don't think has many analogs, kind of at the level and focus that it is. So kind of, I just really believe we all need to bring our part. I don't know what the right solution is for that. I'm showing you what the Swiss solution is because I happen to think about it. And just kind of like, for me, again, the question is not just what can we also do. The question is, how can we really jump ahead? Kind of being in constrained environments really helps. Look, I had a much bigger budget than, okay, the budget at NASA for Earth Science was $1.7 billion per year. I'm only talking about 200 million over 10 years. NASA has much more money, but has not done this. Why? Because they're not putting the constraints on them. Much of it is not about the money. The money is somewhere, you need to talk about the money. But you know, like, we talked about entrepreneurial things. One of the things in my life that I did in the past is I ran venture funds and kind of entrepreneurial activities. The question I always ask people want money is like, suppose I give you the money, what's the next problem you're solving? And the answer usually is something that had nothing to do with money. You actually need to understand the problem. Go solve that problem. And then let's talk about money afterwards, right? So for me, I don't know what the solution is. I think you're doing really exciting work here. I really mean that. I mean, I'm really exciting. Of course, I have a good teacher who tells me how exciting the work is that you're doing here. But this is the kind of work, if done well, will seed thinking all around. And I mean, I'm very open. I don't want to kind of make declarations, but we should be very open to discussions about collaboration and work that we can help each other. For me, one of the reasons I'm standing here is for that reason. I don't know many people who can be as good as you guys are in some of the work that you're doing. So let's figure out how we can benefit, because I don't want to duplicate. Let's just go use the right way. So for me, the question just really is the scarcity that you have in dimensions, like Switzerland is scarce in terms of area. It's scarce. is also a way to actually focus your attention in a way that makes you unique and amazingly important. And so for me, that is really critical. So I just encourage, I mean, frankly, you're doing it already. But I just like to encourage you to continue doing that. Ask the question, what can we do? But ask also the question, what can we do better than others? Because there are solutions to that answer in every case. Does that make sense?
Yeah. All right. Thank you very much. With that, we end the session today. And let's thank Professor Zurbuchen for his amazing talk. So it's lunch time now. We will meet back here at 3 o'clock.